The mainstream media is obsessing over the wrong battlefield. They are tracking export bans on extreme ultraviolet lithography machines. They are counting transistor nodes. They are writing endless headlines about software features and political sanctions. But right now, inside the boardrooms of TSMC, Samsung, and Intel, executives are quietly terrified of something else entirely. They are scared of glass. A single sheet of engineered glass, thinner than a strand of human hair, is sitting at the absolute center of gravity for the biggest hardware shift the semiconductor industry has seen in decades. And while the policy establishment in Washington was looking the other way, China quietly poured over $1 billion into making sure it controls what comes next. On the surface, this sounds absurd. Glass is everywhere. It is cheap. It shatters. It is in your windows, your smartphone screens, and your kitchen cabinets. So why are the titans of global silicon treating it like highly classified munitions? Why is a massive industrial pivot happening completely out of the public eye? And why has an entire nation been building secretive supply chains, filing patents, and retrofitting massive factories around this specific material over the past 3 years? The answers shatter the mainstream narrative. And once you understand what this material actually does inside a high-performance chip, the whole story clicks into place in a way that is genuinely hard to shake. To understand why this matters so much, you first need to look at the invisible foundation everything runs on. For 50 years, the entire computing industry obeyed one simple religion: make transistors smaller and the world gets faster. That formula built the modern economy. It gave us cloud computing, smartphones, and the dawn of artificial intelligence. But in 2026, that rule is breaking down. Today's frontier AI systems demand so much raw computational power that even the most perfect transistors are choking. Engineers have hit a wall, but the wall is not inside the silicon. It is underneath it. Think of a skyscraper. When engineers design a hyper-tall tower, the public obsesses over the glass facade, the twisting architecture, and the systems running through the floors. But none of that matters if the bedrock underneath is unstable. A shaky foundation means the entire structure is compromised, no matter how brilliant the architecture is above it. In the semiconductor world, that foundation is called the substrate. For decades, these substrates have been manufactured from organic materials, sophisticated layers of plastic and resin. They essentially act as high-tech laminated cardboard, holding the chip together, routing electrical signals, and managing heat. For a simpler era of computing, they worked beautifully. But modern AI chips are not simple. They are sprawling conglomerates of smaller chiplets stitched together into massive packages, some now stretching beyond 8,000 square millimeters. That is the size of a large smartphone screen, packed with billions of microscopic connections firing simultaneously at blistering speeds, generating brutal amounts of heat. At this extreme scale, organic substrates physically break down. They are not rigid. When they heat up under the crushing payload of an AI training run, when they cool down, they contract. Do this thousands of times, and the substrate behaves like a fatigued rubber band. Tiny physical shifts start accumulating. Connections that were perfectly aligned on the assembly line begin to drift. Signals that should travel cleanly start to bleed and distort. In the worst cases, the microscopic solder joints snap entirely, and a multi-thousand-dollar chip dies. You cannot see these shifts, you cannot feel them, but when you are dealing with electrical connections smaller than a strand of DNA, invisible is not safe. Invisible is catastrophic. The patches are running out of road. The industry requires a completely new bedrock. The solution engineers landed on shocked almost everyone in the industry: glass. When the concept was first proposed, critics aggressively dismissed it. Glass sounds like exactly the wrong answer. For a machine operating under extreme mechanical stress, it is brittle, it shatters. It is what you sweep off the floor after a mistake. But the glass being deployed in next-generation chip substrates is nothing like a window pane. It is a precisely engineered, thermally stable material designed for the most extreme tolerances in modern manufacturing. Look at the numbers. They are striking. Glass substrates can support up to 10 times more interconnect density compared to today's best organic substrates. 10 times. That is not an incremental improvement. That is a generational leap. If organic plastics behave like a flexible rubber band under thermal load, glass behaves like a titanium rod. You can scorch it, cool it, and load it with mechanical stress, and it barely moves. Its dimensional stability is absolute. Because it holds its shape with such extreme precision, engineers can pack electrical pathways impossibly close together without the fear of them drifting out of alignment. Furthermore, glass conducts heat flawlessly and allows electrical signals to travel with almost zero interference. This means AI processors can run hotter, faster, and longer without throttling themselves to prevent a meltdown. But there is a brutal catch. Making this work at scale is extraordinarily difficult. To route power and data, you have to drill millions of microscopic holes, called through-glass vias, directly through the material. These holes are smaller than a human hair. You must drill them with absolute perfection, without introducing microscopic fractures that could quietly propagate and shatter the chip months later. Mastering this manufacturing yield is an engineering nightmare. It is a massive barrier to entry, but it is also the ultimate competitive moat. This brings us to the asymmetric counter-strategy. For years, the Western policy community built its entire geopolitical framework around one choke point: extreme ultraviolet lithography machines made by ASML. Block the advanced machines, block the transistors, win the war. China looked at that heavily guarded front door, made a calculated pivot, and quietly started building a monopoly in the basement. The strategic elegance of this play is profound. Advanced packaging, and specifically the glass substrate layer, does not require restricted EUV lithography machines. It requires material science, precision manufacturing, and relentless patient capital. All things China has systematically built. Through its state-backed national investment funds, often called the Big Fund, China redirected over $1 billion strictly toward advanced packaging infrastructure. They capitalized on a massive industrial overlap that the West ignored. Take BOE, the Chinese megacorporation that dominates global display technology. BOE already manufactures hundreds of millions of precision glass panels for televisions and smartphones every year. The equipment, the talent, and the massive economies of scale are already in place. Moving from display glass into semiconductor-grade glass substrates is not a reinvention of the wheel for them. It is simply an escalation. By aligning with raw material giants and deploying massive state capital, these companies have been solving the fragile yields of through-glass vias. While the Western press was writing articles about the transistor race, they found the blind spot and they exploited it. But the incumbents are waking up, and they are fighting back with lethal urgency. The moves being made right now by the giants of silicon will dictate who controls the infrastructure of the 2030s. Intel carries the deepest patent portfolio in the world for glass substrates, built over a decade of quiet research. They are weaponizing that intellectual property, positioning themselves as the foundational licensing layer for the entire ecosystem. Samsung is pushing aggressively, synchronizing its materials and electronics divisions to spin up an active pilot production line at its Sejong facility, targeting commercial-scale yields well ahead of industry expectations. And TSMC, the undisputed king of silicon packaging, is aggressively accelerating its glass programs. TSMC currently controls roughly 90% of the advanced AI chip packaging market. They know better than anyone that their entire monopoly could evaporate overnight if they fail to master the glass transition. This is a fierce, hyper-capitalized, and completely undecided sprint. And here is the brutal economic reality of the technology flywheel. A single glass substrate production line costs up to $1 billion to build. Whoever achieves volume production first immediately locks in the biggest AI customers. Those customers provide the capital and data required to refine the manufacturing yields. Perfected yields drive down costs, creating a compounding, structural lead that latecomers will find physically impossible to close. The silicon era was defined by who could carve the smallest transistor. The artificial intelligence era will be defined by who controls the invisible foundation sitting beneath it. We cover the moves that happen before the mainstream catches on. Do you think the future gets decided by the companies printing the smallest transistors, or by the nations controlling the glass sitting underneath them? Drop your answer below, hit like, and subscribe.